Thank you. Today I'm going to talk about gas separation, or in other words, gas concentration. In microsystems, we have various phenomena which are not seen in macroscopic systems. For example, if there is temperature gradient through a microchannel, gas flows from the cold part to the hot part. This is called thermal transpiration flow. One direct application of this flow is a motionless pump called Knudsen pump. In the present talk, we focus on gas species dependency of this flow and demonstrate the capability of Knudsen pumps as gas concentrators. In recent works, Knudsen pumps are implemented as a dime-sized pump using porous membrane or a micro-machined on-chip pump. So our concentrator can also be implemented on these microsystems. To start with, I briefly introduce the thermal transpiration. Gas molecules are flying around in the microchannel, colliding with each other. The distance between two successive collisions are called free path, and the mean free path is around 0.1 micrometer under atmospheric pressure. When we consider a small portion of the microchannel, like this, the molecules from the upper end and those from the lower end may hit the same point on the wall. So, if there is a temperature gradient in this scale, molecules from the hot part hit the wall and then give the downward force to the wall, while some molecules from the cold part, which are relatively slower, may hit the same point but only weaken the downward force. As a result, the wall gets downward force, and as its reaction, gas gets upward force. As the driving force of this flow is momentum transfer between the gas molecules and the wall, the flow speed depends on molecular mass. This species dependency enables us to use this flow to concentrate gases. Now we consider a mixture of gases separated by a porous membrane. When it is hot here, thermal transpiration flow is induced upward, where the gas with light molecules flows much faster than the heavy gases. This is Knudsen pump for gas mixture. Now we increase the pressure in the hot part so that the pressure-driven flow is induced downward. The flow speed of each component is plotted here against the pressure difference. Although we have the pressure-driven flow has species dependency for very small channel, when the channel size is as large as the mean free path, the dependency almost vanishes. Therefore, when we increase the pressure difference, there is a region where the light gas flows upward and the heavy gas flows downward. This is what we call molecular exchange flow, and it is used to concentrate gases. Our design consists of three parts: a pump, a molecular exchange part, and a valve. These two parts have the same membrane whose pore size is around 0.1 micrometers. Then we arrange flow channels along the membrane whose width is 2,000 times larger than the pore size. In the pump, the gas flows upward by thermal translation flow to drive the circulating flow in the device. And in this molecular exchange part, the temperature difference is balanced with the pressure difference caused by this valve, so that the molecular exchange flow is induced through the membrane. As a result, in the upper channel, the light gas increases as the gas flows to the right, and in the lower channel, the heavy gas increases as the gas flows to the left. This results in a large concentration difference between the right and the left end. First of all, we have numerically simulated our device. The simulation is based on mass conservation law, and the flow through the membrane is estimated using the results of rarefied gas dynamics, or kinetic theory. We prepared a 15 centimeter length device and filled it with neon and argon mixture. Then we give temperature difference of 60 Kelvin here and 90 Kelvin here. Then the steady distribution of molar concentration of neon is plotted here. We can see that the concentration at the right end is much larger than that at the left end. For example, this black line shows that the concentration of neon varies up more than 10 to the 5 power. Thus, our device is capable of amplifying the concentration. Now, in order to show the feasibility of our device, we have fabricated the right half of the device. This is a photograph, and this is a cross-sectional illustration. A porous membrane is held between two aluminum plates. One is heated and the other is cool. The flow channel between the membrane and the plate are connected to the outside by these pipes. In the next slide, I show you the detailed structure between these plates. The membrane is made from mixed cellulose ester, which is a similar material to the paper. The pore size is 0.1 micrometer, which is comparable to the mean free path. The thickness is around 100 micrometers. Then we put copper mesh to secure the channel, and then stainless mesh to protect the membrane from the copper mesh. Now we want to know whether the molecular exchange flow is possible or not. In this experiment, we introduce a mixture of helium and neon at the volumetric flow rate of Qn. If we denote the flow rate membrane of neon and helium like this, according to the mass conservation here, we obtain this relation, where Q back is the flow rate here. As we can regulate the Q back by this valve, if this condition, Q back equals to Qn, is realized, then we can expect that the molecular exchange flow is induced. Then, in order to know what happens in the device, we observe the concentration difference between the left end and the right end. The temperature difference is 30 Kelvin. This graph shows the concentration difference of helium gas against the flow rate of gas introduced into the device. As this the concentration difference is positive, we can see that the helium gas is concentrated at the right end. Then we calculated the flow rate through the membrane. The result shows that the helium gas flows upward and the neon gas flows downward. Thus, we have successfully induced the molecular exchange flow. As the size of the membrane is 30 millimeters times 30 millimeters, the flow speed of molecular exchange flow is around 100 micrometers per second around here. Finally, we have investigated into the effect of temperature difference. We have carried out experiment for helium-argon mixture and for the temperature difference of 20, 30, and 45 Kelvin. Larger temperature difference induces stronger thermal transpiration flow and then stronger molecular exchange flow. Therefore, as the temperature difference increases, the concentration difference also increases. Let me summarize my talk. We have proposed a novel design of gas concentrator which uses the molecular exchange flow, and fabricated the device using mixed cellulose ester porous membrane. Then, we have successfully demonstrated the molecular exchange flow and the feasibility of our gas concentrator. In the experiment, we have successfully induced up to 7% of concentration variation for helium-neon mixture and 15% for helium-argon mixture. Thank you for your attention.